Hey, all right, so we're going to continue by looking at electric field lines, right? Now, we would have learned about electric charges and their existence in all different states of matter, being positively charged charges or negatively charged electric charges. Now, field, each charge has a given region around it for which it experiences a given force. And that region, which we're going to find out, is referred to as the electric field. Right? And by definition, we're going to find out that the electric field is the region in which a body experiences a force due to its charge. So it's a region around that charge. Now, namely, we know when we want to illustrate how a proton looks, we draw it as point charge, right? Or we have that of an electron, negative sign in a set of a circle. Now, each of these charges in particular have their own field, electric field. You know, like now we're referring to social distances, everybody wants to stay within their bubble. So the electric charge has its own field around it and generates its own effect. Now, so around these point charges, we said that it experiences a force due to a given charge. It causes a certain things to happen. Now, first we're going to look at the positive charge. Now, the field lines around a positive charge are so designed as if there was another positive charge very close to it. Good. That is how you design the field lines of a positive charge. Now, what that means is that if you were to put another positive charge next to this field, this proton, what is going to happen to it? What is going to happen to this charge? And we're going to find out due to the one of the properties that we learned about electric field that like charges are going to repel. So basically, if we were to put this charge here, it is going to push it away. It is going to cause it to move outwards in that direction. So if we were to put a point charge anywhere else around, we're going to realize that it causes each time that it's going to push these charges away from it. So there goes the electric field of a positive charge, right? And as you can realize that they look like the spokes of a bicycle wheel in terms of being a radial charge, radial field. Good, and they all point away from that positive charge, right? They point away from the positive charge. Now, similarly, we're going to design that the electric field of a negative point charge. How would it look? So we use the same concept whereby we're going to place a positive charge. If we place a positive charge just very close to this negative charge, what do you expect it to do? Right? So this much larger negative charge is going to attract that smaller positive charge. So it's going to pull it inwards to it. Good? So if we were to take this positive charge and place it all different points around, we're going to realize that it keeps attracting the positive charge towards it. No matter where you place that positive charge, they're all attracted towards the negative charge. And therefore, you realize that it gives you a similar nature in terms of a radial pattern, but the key element here is that these lines point towards the negative charge, right? These lines point towards the negative charge, therefore, this represents the field lines of a negative charge. So anytime you place a positive charge anywhere around here, it's going to be attracted towards the negative and be repelled from the positive. Good? Now, what we would have learned earlier is that unlike charges are going to be attracted to each other, right? So a positive charge is going to be attracted to a negative charge, that they pull each other in. So basically, how does that look when you want to draw their field lines? We're going to realize that the line goes straight from the positive charge towards the negative. It goes away from the positive and it goes towards the negative. Away from the positive towards the negative. And this happens continuously, different positions. So you can have them going around. Some cases they're broken. So they go away from the positive but towards the negative. Away from positive towards the negative. Alright? So this represents what happens in the case of a positive charge becoming very close to a negative charge in the case of attraction. Attraction occurs. Right? Attraction occurred in this case. Now we want to understand what happens with repulsion, right? And repulsion only occurs when you have two charges of the same kind coming very close to each other. So in the case of, let's draw a proton coming close to another proton, right? A proton coming close to another proton. Now, in the case of a proton coming close to another proton, is that these charges are going to go away from the proton. They both go away from a proton. But I want you to notice something happening here. We have this line coming and this line coming towards each other. And what you're going to realize happening is that they don't meet because they are of similar nature. Right? So this is what happens when you have the case of repulsion. Now, in this case here, in this region, is a region where there's no effect is going to be happening at this point. There's no bit of attraction or repulsion. Basically, it's a null zone, right? So this is basically what happens when you look at the electric field lines of different point charges. So you have the positive charge, the negative charge. The positive charge where the field lines go away from the positive charges, and the negative charge is where the field line goes towards these point charges. In the case of having unlike charges that they attract, this is how they appear, where the lines flow directly from the positive charge into the negative charges. And in the case of repulsion, where you have two like charges being very close to each other, that these lines never intersect at any point, right? Where they flow away from each other, leaving a dead zone in the middle. Now, just before we finish, there's one more we need to look. These are all point charges, but what happens if you have a linear or an electrode, right? What happens if we have a positively charged electrode? As we know that the field lines appear like they travel away from, and they're going to travel in a straight line path away from that point charge. Good? Same thing happens if you have a negative charge electrode, that these field lines go towards a negatively charged electrode. Good? In straight lines. So that concludes looking at field